Okay, so I'm delighted to introduce Erol Gelenbe, our speaker today. So Erol is infinite dimensional, so I will only give a projection in terms of countries, for instance, and a few topics. Describing his career would take the whole talk, so I will not indulge into this. But so as you see, Erol is active. There are already 3 countries on this slide. Poland, he's a member of the Polish Academy of Sciences and the head of a lab there. He's quite active in UK also, and active also in I3S in Sophia Antipolis. Where is Godong? Godong is here. So Sophia Antipolis. Godong will go to Sophia Antipolis in a few weeks.
You get better weather.
Yes.
I can guarantee that.
But this is a tiny projection. Erol was active in several other countries, including the US, where he spent a fair amount of his academic career. In Belgium, he has also old and fundamental ties with many countries in Europe, including Italy and Turkey also, and many other that I will not cite. In terms of topics, he started his career working on the modeling of computer systems and communication systems, and then evolved to a broad set of questions, and you see some of them projected here. Random neural network being one of them, and cybersecurity being another one. So there are many other dimensions I will not have time to cite. I would like also to stress that he has been very active in helping the several governments, including the French government, for the shaping of education in a variety of topics, and also in a variety of universities and institutes in France. Erol.
Thank you very much, François. I'm switching to English, which actually was the first foreign language that I learned. I can't say that Italian is a foreign language to me because my mom was Italian. So I learned Turkish and Italian when I was very small. But the first foreign language was actually English, which I learned in primary school. So anyway, on we go. As I was speaking in French, I just mentioned one name, and I didn't say too much about that. Lapicque. This person was perhaps the person who produced the first spiking neural network model. It was very simple. It was for one neuron. But he had this intuition, perhaps even measurements, in the late 19th century. I think he lived in Strasbourg or Nancy perhaps. And he and some of his collaborators, I think, published 1 or 2 papers where they were describing the spiking behavior, although they described it more as a step function behavior. So they might have been mixing the spiking behavior with the transition on-off switching behavior of a neuron. But it's kind of very interesting. And what I wanted to say related to Lapicque, although he didn't get any big awards, I think he was nevertheless a member of the French Academy of Sciences. I'm not sure. But although he didn't get the big awards, but at that time, there was the first important work happening in Europe and in the world, of course, on neural networks and neurons, and the first Nobel Prize in this area, which was given to an Italian, Golgi, at the University of Pavia, and to a Spanish person, Ramon y Cajal, who was in Madrid. So this is an interesting historical reference because I'm very interested in the spiking behavior of neural networks, and then that has been left aside a certain amount of time. Now back to my talk here. The problem that I'm looking at here is the issue of detecting cyber attacks. Cyber attacks are plentiful. I mean, they're happening all the time. And the strange or perhaps interesting thing is that because of the rules about the manner in which we are allowed to look at traffic in the networks, we're not really allowed to look at inside packets unless you are the owner of the traffic. Okay, so then you can the stuff is automatically deciphered for you, and then you get to see it. And then if you are smart, you can detect whether there's malware in there or there's an attack. So the only real way, because we're observing a lot of traffic, so if you're detecting attacks, hopefully you don't have the attacks happening to you all the time, but they do happen sometime and frequently. But nevertheless, you can't, because of that, say, I'm going to read whatever traffic comes into this system, I'm going to look at it and read it. Well, that's impossible. You're not allowed to do that. Only the end users are allowed to do that. So what happens then is that you have to find other methods for finding out whether the traffic coming into you is harmful or not. And what can you do? As you know, all traffic, quasi-all traffic is packetized. So what we do is look at packet streams, okay? And from packet streams, we try to detect cyber attacks. A lot of my work is related, although I don't just work on this, I also work, for instance, on energy optimization in computer systems or networks. So how you can dynamically, for instance, allocate tasks in a system so that you can guarantee that the amount of energy consumed is minimized. That kind of thing really fascinates me, but I don't just work on, and that I do with mathematical models rather than with AI. But in this context, in this particular context, I work with in the European research frameworks, and this involves always working with industry. And the nice thing about working with industry is that in a team of researchers or engineers working on a project, you have use cases. So everything we do ends up being demonstrated in a use case. So this particular work, which is not completed yet, but this particular work will be demonstrated in a smart cars use case, which will be run by a partner who actually has a large area, a campus with autonomous vehicles going around, okay, and controllers for the autonomous vehicles. And this is a company called Tecnalia in Spain that works for the European automobile industry and has all that stuff. Okay, so I'm trying to tell you a little bit about the context. Now let's move on. Despite or because of this very practical type of outcome. Now, how do I go down? Okay, fine. So despite this very practical outcome for the work, okay, we'll see how that goes. Despite that, what we tend to do is actually published in refereed journals, especially. And I'll tell you why journals rather than conferences. It's because this work that I'm doing is part of activities inside an institute of the Polish Academy of Sciences. And every year they look at your publications and they put points on them based on where they have appeared. Now, of course, it's a bit of a bureaucratic process, okay? And then the budget that the institute gets is a result, more or less, of the total points that the total number of researchers in the institute accumulate, okay? This sounds silly, but of course, these points change with time. But you have, of course, you're going to say Nature has the top points, 200 points, but so does the Proceedings of the IEEE, which has 200 points. So does IEEE Network, which has 200 points. So has the IoT, the IEEE IoT Journal, that has 200 points. So, but then other things like IEEE Transactions and Information Forensics, which is very good, might have 140 points and so on. So basically, they give you points, and the conferences are much more controversial with respect to these point-based systems. Of course, you have CVPR and so on, these conferences, which are very well known, but it's more controversial. And we write we submit to journals and write journal papers because we know that this is going to be valuable for our institute. And with there being open access and so on, it's fine. You know, we find this as a good way to proceed. So this is a list of papers specifically related to my talk today, which includes early work in IEEE Access on the development of the algorithms and results with different attack data sets. Then we have, for instance, IEEE transactions and information forensics, real-time online type things, and so on. So it gives you an idea. And the last paper here with my Palestinian student, Mohammed Nasser Eddin, is really at the core of this particular presentation. So a lot of the things that are in the presentation, you can find them in that paper. Okay, now I'll try to move on. That doesn't do it. This one, oh, no, that goes the other way. Okay, fine, all right, fine. Perfect. Oh, am I the opposite direction?
Yeah, it's counter.
No, anyway, on the left-hand side, you see an idealized representation of an edge system. Now, edge systems are very popular today with people doing 5G, 6G, beyond 5G, 6G, etc., because most of the communication systems we have require substantial computing at the level of the base stations. We're looking at, edge systems. And of course, edge systems are also very useful for instance, controlling a large Internet of Things network. Suppose you have a building, for instance, with a lot of sensors and so on. You're necessarily going to have an edge system somewhere sitting, which is an architecture which can extend, add more processing power as needed, add more applications by adding more processors and software and so on. So you're going to have an edge system. And the security, that edge system will contain a dispatching platform, which will send the work. Now, this is an idealized kind of semi-queuing theory type representation. The red boxes represent the edge machines, which might be, for instance, Raspberry Pis or Intel cubes. We have an architecture like that in Poland in the lab. And next Monday, I will be there. So you have this kind of architecture, and the architecture must be protected. And the point of protection is typically at the dispatching platform, because it's the part that dialogues with the outside world, okay? Because attacks have to come from somewhere. The other machines are isolated in the sense that they get their stuff from the dispatching platform, but the dispatching platform will be connected, as you can see on the right-hand side, through a switch to many different things. And that is where you need to put some protection, okay? Now, when you look at so you have a server which represents a dispatching platform, and the server is here. What does it have? I mean, it's very schematic. You have the network processing, SNMP type protocol, and its software, which is looking at the packets coming in, okay? At that level, you can't start examining because, first of all, you must get the packets in before you can actually start processing. But behind that, you will have an intrusion detection system, okay, which will look at the individual packets, okay, and kind of, as they come along, try to extract some characteristics of the packets. Use those characteristics to decide whether this is an attack or not, okay? And then behind that, if the packets clear the attack detection framework, then they will move on and be used. They will be sent to this application, that application, and so on and so forth. So that's how the overall organization looks. Now, between the server and the switch, you see a box. Now, that box was the subject of my talk last year here. It was a special kind of traffic shaping policy. Okay, a traffic shaping policy, very simple one, which even when the attack happens, allows you to process the packets at a rate, which then allows the rest of the system to work. Because most attacks are associated with a flood of traffic, and they can overwhelm you. So you need some form of control, traffic shaping, to make sure that you don't drop good stuff, but on the other hand, that you are able to pace it in a manner which allows the, for instance, intrusion detection system to work properly, and so on. Okay, and I'll show you some data about that today, because I have much more data now than I had a year ago. Okay, so we move on. I'll skip most of this. Now, the intrusion detection system, I should say, excuse me.
Could you say a few words on where this IDS is in the flow?
It's sitting in the server. So you have the smart QDTP, and then you have the server, and the server is this box. So the traffic shaper, we have implemented it. Everything that I described has been implemented, is implemented, and is used for our experiments. Now, the smart QDTP is put in a Raspberry Pi, sitting in front of the server. And this Raspberry Pi only does that, so it can manage it. It just runs this algorithm and passes the packets on to the server. And then the server has the network management, the traffic network port management software. And then it has, the protocol software, let's say, and then you have the intrusion detection system afterwards. Okay, I will skip all the math associated with the neural network model that we use, because if I did everything, I just wouldn't get on with it. So I will be skipping all that and can tell you a little bit in vague terms as we move along. And then I'll try to tell you, okay, and now we are at the intrusion detection system. The intrusion detection system kind of said vaguely that you start, first of all, by collecting metrics on the packets, okay? So you collect metrics, but you have to do this in real time. So we have a sliding window, basically. A sliding window of I packets. You can vary I in the algorithm. I is of the order of 7 or 8 or 10, that number. Okay, so you don't keep a long-term memory in this. It's a fairly short-term memory. It's a typical sliding window. And in this sliding window, you're collecting what? You're collecting the amount of bytes per packet. You are collecting the number of bytes in a collection of packets, in the window of packets. And you're collecting the inter-packet arrival time. Okay? So these three things are being collected and are being used as an input to a neural network. But they're being used as the discriminators for a potential attack detection. Okay. Now, why would you look, for instance, at the inter-packet arrival time for that? The reason why you look at that is typical attacks are not based on TCP. Why? Because attacks usually provoke losses, and if the attacker is faced with is running a TCP property, the attacker will back off. So it's completely out of interest for the attacker to use TCP. You'd say, well, why don't you use the attacker's IP address to identify attackers? Well, you can't really, because no attacker gives you their true IP address. They're spoofing them, so that's not usable, right? But looking at how fast these packets are coming is very important, especially because a lot of attacks are run by botnets. So they're automatic attacks. It's not someone just making an attack by hand. And what they have is they create an automatic attack, which then, if it is successful somewhere, starts propagating more attacks. So it's repeating itself. So you're going to have at some point, it's going to be a huge flood. And because of that, you're going to have short inter-arrival time. So you're looking at that. And then, of course, if these packets are carrying our attack packets, they will try to overwhelm you with malware. And the malware is programs. Okay? So that's going to be a lot of bytes. So all of that is indicative of an attack, right? Now, of course, we don't assume that everything that comes in fast and everything that has a lot of packets, et cetera, is necessarily malware, which is why we train this network that you see in the middle, the neural network in the middle. We train it, first of all, with normal traffic. How do we know it's normal? Well, we call upon data sets of normal traffic. Okay, we call upon data sets of normal traffic, which are calibrated data sets, often generated and obtained by US organizations often US military organizations, but they put their data sets out publicly. We use those, and they are labeled. They say, well, these packets are normal because they have opened them. These are fine, and these packets are attack packets, and these packets are normal, and these, et cetera, et cetera. So you have big calibrated data sets, and we use those, and with those, we train this network. But how do we train it? We train it only on the normal traffic. We're not trying to learn all kinds of attacks. We're trying to learn normality. And therefore, we have an auto-associative training of the network. Okay? We have an auto-associative training of the network where we tweak the parameters, usual minimization of cost functions. We tweak the parameters so that the difference between input and output is minimized. So between what comes at the input and the output should be minimized on the normal traffic. And then during the use of this discriminator, if there are strong differences between the input vector and the output vector, then we assume there's an attack. And again, we do this on a window. Okay? And again, the window is of the order of 7, 8, 10 packets. Okay? In fact, we're running right now, I'll get to you. Right now, we're running very precise experiments on how these windows should be chosen. Yes, please.
I remember in the past, I worked in some projects where people from around were looking at the profile of the traffic, and they were trying to detect traffic anomaly. It's something that what you do here.
Yes.
The problem they had is that it depends a lot on the location where because the profile of the traffic is not uniform.
Absolutely.
The location where you are.
Right.
So here you train on some data set. How are you sure that the normal traffic that you will have in reality will not have some deviations with what you
when you work with AI machine learning, you're never sure. You can only reproduce statistics about what has happened, okay, which is what we do. However, we run, in addition to training on data sets, we run attacks in the lab. So we have not seen so far a disapproval of this approach, okay? So we actually run on our testbed, we launch attacks, which we make up ourselves, okay? So we do that, and this seems to be working. So that's all I can say, right? So yeah, now about the neural network itself, it's a stochastic model, okay? So it's actually a queuing network. It's a queuing network with, in this case, 3 kinds of customers: positive, negative, but also triggers. Triggers means that, if you wish, from a neuronal viewpoint, if you have several neurons, okay, and they are all excited, together they will excite another one without necessarily sending a spike, okay? And this is called, something exists in nature, which is called soma-to-soma interaction. Now, we use that trick to increase the accuracy of the model, because this trick allows us to replace large numbers of cells by equivalent transfer functions. Okay, through the analytical properties of the model, we can take limits and say, here I would like to put 100 neurons to get accuracy. Why don't I put an infinite number of neurons? And then, rather than simulate 100 neurons and compute for 100 neurons, we compute the transfer function of those neurons. Okay, and this allows us to have actually a very large network, but with a small computational cost. Okay, with a reduced computational cost. So that's kind of a trick that we do, which works very well. So it improves the accuracy, in fact, by reducing the computational cost, because we can predict the transfer functions. So that's thanks to the G-network properties. But anyway, so that's what we do here. So we have a network which, in effect, is very large, but it has been simplified through transfer functions. And so it's computationally quite nice, okay? And we show, empirically, we show that this is actually producing, fairly accurate. Now, this is more details about the pre-processing, about the way we take the decisions by comparing input and output, and doing this over a certain number of packets flowing through the input. and through, some statistical boundaries that we set up. And the type of accuracy that we get is quite good. Now, this is from a botnet attack data set that you're seeing here. And it's dealing with many different IP addresses that are perceived in the traffic. So it's the IP addresses are varied, or the origins are varied, because it's a botnet attack, of course. And we compare different methods. So the top one, AADRNN, in the list, I didn't say the top one in quality, but the top one in the list is what we developed. Then you have the KNN standard method, Lasso well-known method. And we see that accuracy is very good in all of them. Interestingly enough, where the auto-associative model that I just described works very well is in reducing the false positives, okay? Which is very important because false positives are very bothersome because, as you will see in a few minutes, as soon as there's a positive, true or false, because you don't know, of course, you don't know, you see an alarm, and then you have to react on the system and do all kinds of bad things. So you want to limit your false alarms. So this says that this method is, the same accuracy, perhaps slightly better than the other ones, but the main point is that it does much better on the false positives. Okay, so what does it mean? It means that it has learned better in a certain sense. It has learned better the normal traffic, which it recognizes. This is basically what it means. Sorry about that. I'm always pushing the wrong button. Now, then we take our method and we test it on a different data set. It says 99, but the KDD Cup 99 is a name. There are 22 versions of this. Okay, so we don't use the original data set. This is a data set that has evolved over time. And what we're doing here is we're looking at accuracy for many different types of attacks, because this data set contains many different types of attacks. And we say, are we doing well on all of the attacks? Well, the answer basically is there are 37 types of attacks in this data set. What we see actually is that we do well on, say, 2/3 of them. We do well or very well on 2/3 of them, and we do badly on the other ones. Okay, so we can't claim that we are perfect, okay, but it seems to work, okay? And on the right-hand side, we compare ourselves, AADRN, with support vector machines, which is a fairly costly, time-consuming type of machine learning technique, and we see that we're doing better than support vector machines, okay? So when you want to publish a paper here, you always have to show on data sets how you do compared to the state of the art and compared to methods that may be more costly computationally, okay? And in the previous slide, you can also see on the right-hand side the computational cost issues. But for execution, not for learning, execution costs. And you see that we are not too bad. Lasso is faster, but we're much better than KNN. So we're doing kind of reasonably well with respect to the computational time for the execution of the algorithm. So it's a fraction of a microsecond on the server. Okay. This is per packet, of course. Now, as we go along in the other direction, no, sorry. We want to have a more careful look at what is going on at the traffic level when an attack happens. So it's very interesting because, as you would expect, this is a 10-second attack. That's not a long attack. It's a very short one, actually. It's a 10-second, very short attack. And if you look at the queue length at the input of the system, it's gone up to 400,000 packets in a buffer, huge number. And if you were just going to roll them out at the rate at which this server can process them, it's a huge amount of time as well. So that's very bad news, right? I mean, you need to do something. That's why you do mitigation, you drop packets and all kinds of stuff when there's an alarm. But so this is, if you don't do anything. And the right-hand side shows you The top figure is quite interesting. What you're seeing is that while the processing time of most packets is okay, you have huge outliers, okay, very large processing times for packets, and things get worse with time, probably due to the backlog that's built up. So basically, this is one way of looking at the effect on the system. But another way of looking on the effect of the system, sorry about that, is through the packet analyzing time per packet for the intrusion detection system. Okay, the intrusion detection system examines packets, and if the traffic is normal, this is the distribution of the processing time per packet. Okay? If it's an attack, it becomes heavy-tailed. In fact, you don't see all the tail. If you, for instance, you don't see all these points that are huge peaks in the previous slide, but you're seeing that everything has shifted to the right. Okay. Substantially. So the system has been slowed down by the attack. And that's a very important part of the whole process. Okay, which is one of the reasons. So the attack is not just malware coming along. It's just basically slowing the server down. Sorry about that again. Okay, and that's where the QDTP algorithm comes in. And what is the property of this algorithm? I think the main property, which is of interest, is that if you choose the main parameter of this algorithm is a quantity you might call D, large D, and this D has to be shorter than the service time of the packets. Okay, you have to set it up in advance to be shorter to obtain stability. Now, if you do that, then you can show that the end-to-end delay is no bigger than the first in, first out delay. Now, in fact, we have recently proved and submitted that the delay is not shorter than or equal to, but exactly equal. Okay? This is recent work, so it's not an inequality that you have on the right-hand side, but equality. That means that the traffic shaping does not change the end-to-end delay, which is nice. Not really slowing down anything from an external viewpoint. You're not changing things, okay? And you're not dropping any packets. You're just playing with the way you push them out. And that's the trick. And as you go along, oops, sorry about that. You want to see how what it does in practice. Well, what it does in practice, in red, is the input queue length without this traffic shaping algorithm. In blue, you have the queue length with. Okay? So basically, what you've done is at the entrance of the intrusion detection system, you have removed the queue. But where is the queue? It can't have disappeared. It's at the input of the traffic shaper, okay? Which is where you should be dropping packets now if you're dealing with this. So where are we? Oops. So now let's look at what has happened to the processing time per packet, and what you observe now is that left-hand side, right-hand side. Left-hand side again is the distribution of the processing time per packet in normal traffic conditions, and right-hand side is in attack conditions. Okay, so basically what you've managed to do is kind of reduce. Kept the processing time centered around a fairly small mean. So you have stabilized the system that way. And I think the numbers are there. So you basically are getting average processing times in normal conditions of 2.97 milliseconds, in this case, variance, etc. And now you have 3 milliseconds. So you've done better. In terms, you don't have a huge increase, a 50% increase or 100% increase. You have only a few percent increase in the processing times. All right, so so much so for this part, and you can look at other characteristics. And now the question is, fine, okay, you could drop all the packets at the input, Is that a good idea? Well, the answer is no, because if you drop everything at the input, you're also dropping off a lot of good stuff. So what do we do? So now comes the other part of the thing where there's absolutely no machine learning. It's just standard optimization. We introduce a method for dropping packets based on sampling them. So that you don't, first of all, as soon as you have an alarm attack, you drop whatever is in the input buffer. Okay, but that's, just after the attack happens. So you drop those, whatever is there, you drop. But then what you do, whatever is coming in, once you've dropped, again, you're checking the packets. Okay, and as long as you have an alarm, you drop. So you repeatedly drop. Okay. On the other hand, you do this at intervals of m packets. That is, you don't do this for all the packets, but you do this for intervals. Why? Because having an alarm tells you that this is going to go on for a while. So you jump by m packets, then you study again. If you again get a response that there's an attack, you drop again, and then you jump m forward, okay? Until you get an answer all clear, no attack, okay? Doing that, of course, you must choose your m well. So this is the scheme that I've described. And what's the cost? There are two kinds of costs. One is the overhead of processing packets. So the sampling each m times means that you're going to do less processing, okay? On the other hand, what's going to happen in the last part of the last sample that you take, when it says all clear, if m is very large, then you're going to lose a lot of good packets. So what you want to do is a compromise between the loss of good packets and the overhead. And that's what the cost function is. And that allows you, defining a cost function, allows you to compute, to predict what the optimum value of m should be. And above, you have the optimum value theoretical. And at the bottom, you have the optimum value experimental. So we run experiments and see how well the two fit. And we see that we are in the same ballpark. For instance, you see m star equals 100 theoretical, m star is 127 practical. So that's in the experiments, we say, where was the minimum? Okay, and we repeat the experiments 10 times, 20 times, 100 times, etc. So we're doing this experimentally, but the analysis tells you this is what you should do. And then the experiment, and this is kind of a classical performance evaluation type analysis. And then the experiment tells you, well, this is all right because it's not too far off. So that's the general idea. We have a lot more work to do. Recently, we have been looking at federated learning approaches in the context of systems where, for instance, if you're looking at a vehicular system, okay, many cars, and you're interested in attacks, obviously all these cars don't belong to Renault. Some are Renault, some are Peugeot, some are whatever, right? So they will not share what is happening to them. And they will not even share necessarily how they do it, okay? But you can perhaps share weights associated to neural networks that describe what's happening. Okay? So we have done that and published work on what happens in federated learning. And one interesting result, first result that we have, this is at the end of 2024, we have a paper in the Elsevier IoT journal. And why Elsevier? Because Poland has a free open access agreement. And the journal has good impact factor. So we get a good number of points for that. But anyway, so and we have an interesting result, which says that when you aggregate in federated learning, at least for these data sets that we used, we shouldn't aggregate with everything being treated equally, but we should aggregate with those who look like us. There are all kinds of explanations for this, but you can also argue against this idea. But basically, we're seeing that aggregating with weights which are similar to you gives you better results. than aggregating with everyone equally. And I suspect that that's due to the variances that are involved. The variances, the differences, and this, so, you know, when you have aggregate with a lot of different things, then you may have a nice average, but the variance is going to be bad. And therefore, in many cases, you're going to be wrong. Right? I mean, that might be the intuitive explanation. So that's one area we've been working on. We have started looking at the energy consumption issues of all of these attack detection techniques. And in 2 months' time, I have to give a talk at Gelenbe University where I'll be presenting results on how these things generalize supply chains, which means I've started working, but I don't have all my results. And the big question, of course, in many of these things is, how about vulnerabilities in the learning process? You know, how can you attack actually the learning process itself? And I must admit, I have done nothing on that yet. Well, thank you. Thank you very much. I don't know how I'm doing just about right on time, I think, in my allotted hour. So I will pause for questions, which you may ask in one of several languages. I prefer Turkish myself. Yes, sir. Questions? Whoopee!
Hello.
Hello.
So thanks for the talk. It was very interesting. And I have a question about your theorem where you show that if D is smaller or equal than the service time per packet, then you do not alter the end-to-end latency.
If D is less than or equal to yes. In fact, D can be adaptive. So it can be a D sub n less than or equal to S.
And D is the execution time of your predictor, right?
It's not the execution time. D is the delay time. The predictor is very simple. I mean, the algorithm is very simple. You say, I will impose at least D time delay to the packet.
Because I was wondering that the service time of the packet may be very, very, very small. Because if in the picture,
no, it will not be very small. The service time of the packet is in the intrusion detection system. So in the best of cases, it's three milliseconds.
Okay, so it's the one. Okay.
So what you do is you, in the best of, I mean, the smallest value is known because that's when there's no attack. So what we do is we put it D less than that.
Okay. And in the slide, maybe 5, I think.
And in fact, just using the intrusion detection system service time is optimistic because you will also have the network protocol at the input.
Okay.
So at the end of the day, it may be several. You know, if the processing time of the intrusion detection system is 3.2 milliseconds at the best, or 3 milliseconds at the best. There'll be at least 1 or 2 milliseconds in addition because of the software. So taking D smaller than that is safe.
Okay. Yeah, because for instance, in the slide number 5, that you
number 5. What?
Yes.
How do I go to slide?
One by one, I guess.
5 at the beginning.
Yes. It was in the first part of the.
Oh, this is another talk. Sorry. I'll do it in a more quicker way.
Yeah, maybe, yes. No, because I was curious about, there was a graph where you had the packet numbers there. And in the timing, I was wondering about, for instance, this, yes, also the next one is okay. The following one.
This one?
Yes, here, so packet number. Here you show, if I look correctly, is 140,000 packets, right?
Yeah.
And I was wondering about the input rate because I work on high-speed network systems, and we deal with tens of millions of packets per second. So this corresponds to a window of maybe a fraction of a second. And
at the network level, but not at the server level.
Exactly. So
yeah. At the server level, it's much slower.
Yeah, exactly. So I was wondering if this approach can also.
You know what you see there? You see a 10 millisecond, sorry, a 10-second attack, and you see it's gone up to 400,000. So that gives you an idea about what the and this, of course, is measured also on the server. So this is the effect only of the protocol SNMP.
Okay, so basically your system is end-to-end, and in this particular work, anything can happen within the network.
End-to-end means from the SQTP, from the Raspberry Pi box that contains the shaper, all the way to the exit of the intrusion detection system. That's what end-to-end is in practice, in this case.
Okay, because yes, I was wondering about what is the pure regular rate that these systems can handle, because having IDS performing.
Well, you see, this system, the way in the lab, for instance, we connected to IoT devices.
Okay. Yeah.
So you can think about the rates yourself there, because the normal ones will send you perhaps every second. Then the ones that are that have been compromised may send you much more, but they're not coming in from fiber optics in the internet. They're coming in, say, from an IoT network.
Yeah. I will send you some pointers, because we had a work where we tried to do actually classification of network functions. So instead of detecting attacks, we detected which kind of function is being executed, and we could not use neural networks, not even these simple ones, because of the execution time. The inference time is very it's actually much greater than the processing time per packet. So we had to
Well, in our case, we know exactly what it is. It's 3 milliseconds, which is a lot.
Yeah, we didn't know that, and so we had to use an indirect approach. So where instead of having the information about traffic that you had, we correlated it with indirect measurements. So for instance, the CPU measurements that are a proxy for what is happening on top of the application. So, and in that case, we could use neural networks for doing the prediction.
I see. So it's very interesting, because you are doing something similar to what we're doing, but you are actually using the result of the processing delays.
Exactly.
As an indicator of an attack.
Exactly. And we didn't have the...
While here we're saying when there's an attack, there's a big processing delay. And what you're saying is if there's a processing delay, there's an attack.
Exactly. Exactly. And we didn't have the theoretical results that you have there. And I do not know if that could apply, because we are within the network and we deal with tens of millions of packets per second, which means that every packet has a 5 nanoseconds. It's 5 clock cycles of time for processing a single packet. And I mean, it's interesting to say if that's that boundary, that lower bound can still apply even in such stringent times.
Of course. Of course, it's a mathematical result.
Yeah, definitely. Yes.
And to make François happy, we've applied the stationary point process theory to analyze the system. We have just...
Thank you very much.
Yeah, thank you. What you say has another thing that kind of strengthens my initial statement. The way you do machine learning depends very much on the context and the data sets. And claiming that you're going to do this with beautiful data sets is just nonsense. Most of the time you can't. I mean, you have to rely, especially when you put them out in the application is kind of you don't know what you're getting.
Hello, thanks for the talk. I have a question about the input variable for detection. You use the flow variables. Yeah, to the intrusion detection. So it's flow variables, like inter-packet arrivals, frequency.
In all of these experiments, the 3 metrics I mentioned are weighted equally. Now we're doing some experiments where we're seeing that we shouldn't have, that it's better not to weight them equally. But anyway.
Yeah, so my question is tangential, because I see and I receive a lot of journal paper. Perhaps people want polish points or other forms of rewards by sending to journals, but it is always about turning traffic traces into images, grayscale images, and using pattern recognition via ordinary neural network models to get results which are always about 99.5%. So I was wondering, to your experience and understanding of the problem, how much does the input representation, so whether metrics are sufficient, whether like pattern recognition is a more advantageous
Yeah, we started with more complicated metrics, and then we simplified them. That is, we saw that having a greater dimensionality on the predictors was not really useful. So that's why we ended up with 3.
Yeah.
So we tried, going to higher dimensions and so on. And then we saw that, well, what was important though was it was more important to have a good network than to have high dimensions. And that's where we started using, because before that we had like we were using more like a standard backprop feed-forward network. And then we kind of went into a more sophisticated network to increase the accuracy. And we saw real increases in accuracy that way.
And I guess also a selling point is the fast execution for the spiking kind of network, which is smaller and more efficient.
Yeah, of course. As your dimensionality increases, then you're going to have a much larger network, slower, both learning and slower recognition time. Now, this approach, we have implemented it in an online learning approach where we're updating the weights as it goes along. Okay, and that is in our last year paper, 24 paper in IEEE transactions on information forensics and security. So you can find it there.
Thank you very much, Commentator.
Thank you. Thank you. I'm very pleased with the questions because it shows people who are actually very much engaged in similar problems.
Thank you for your presentation. I had only questions about false positives because you said it's one of the strengths of your approach. And in the past, we did work on similar network data. And we used a simple autoencoder, which is similar to what you've done here. But I was wondering, like, what are the characteristics of the ADRN that improve the autoencoder?
Yeah, that's what I said. So this autoencoder has, although you have 3 inputs, okay, each node is a cluster of an infinite number of neurons, and the trick is not to represent them as an infinite number of individual neurons, but represent them by a transfer function. Okay. So that is what has initially we used a very simple, as I said, we used a very simple structure, and it wasn't working well with backprop. And then we started using a much more sophisticated structure, and that's where we got the far better accuracy.
Okay, so
we're getting much nicer approximations of the data.
Okay, and in terms of testing, I mean, so you mentioned about the test bed where you run attacks. But where did you get the normal traffic from? Oh, only the data sets or?
Yeah, well, we do 2 kinds of things. So everything I showed you today is based on data sets, publicly available data sets that you can get. Just go online and you find them. There are references in our papers. You click on the website, you get the stuff. Okay, so everything I've shown you is based on that. Why do we have to use that? We have to use that to get past the referees.
Yeah, I know.
Okay. On the other hand, we also do run experiments in the lab. But when it's in the lab, it's necessarily synthetic attacks. But there are things which resemble the behavior of attacks. And we corroborate. But those things are not publishable because I've done in my lab my data set.
So this brings me actually to the question about the false positive here, because usually these data sets are quite imbalanced. And the reality is that you have much more legitimate traffic than you have attacks.
Of course. Of course.
So then,
not always, because the botnet attacks, first thing, botnet attacks are not stationary. Okay, so at the beginning, very few attacks. At the end, many attacks. Why? Because the botnet is spreading. And you see that in the botnet data. The other thing we've tried to do, for instance, I've not talked about this here, and it was in the slides after I said thank you. Okay. In those slides, we are trying to infer the botnet structure. We're doing an inverse problem. So we look at the data sets and we're trying to construct the structure of the attack, which is the inverse problem. What is the math behind the attack? What is the Markov chain of the attack? Okay, things of that nature. So we do that as well. And we even have a paper out on that. So yes, you're absolutely right, but the attacks are not stationary. And not only, but on the other hand, what you say is not completely true because it's not stationary. So saying there are less or more doesn't mean much. It depends which period. And the botnet propagates. So if you see this in the botnet data, that the botnet traffic increases and the number of nodes involved in sending traffic, attack traffic, during a botnet also increases as you go forward.
Okay, thank you.
Basically, being able to ask a question is based on throwing the microphone and being able to catch it, which is the hardest part, except online. Thank you. Thank you very much for your time and for coming here. And including people who had other things, more important things to do.